Sound energy, and speed. In this lesson, we'll be covering hearing sound, creating sound, moving sound, and the speed of sound. If a tree falls in the woods, does it make a sound? Of course it does. When the tree falls to the ground, it generates a vibration, which creates sound waves, whether someone is there to hear them or not. A tree will make a sound in the woods, regardless of whether someone's there to hear it or not. Sound. Humans can generally hear sound waves with frequencies between 20 and 20,000 hertz, or otherwise known as 20 kilohertz. Sound is simply the transfer of energy caused by vibrations between particles with and across mediums. Creating sound. A sound is created by a source, which creates expansions, sometimes called rarefactions, and compressions of air molecules. Note, the particles only vibrate. They maintain their original areas while transferring the energy away from the source. With that said, if someone is standing here and talking to someone over here, 10 meters away, the air molecules might move a little bit. They might move from here to here, the individual air molecules, but they're not going to move all the way across. What happens is that this air molecule moves this air molecule, which then causes this air molecule to move, which causes this one, and so on, all the way down to the person listening. And you can see that in our diagram here on the bottom. We get a source, so in this case it's a radio. It's making a sound with a certain amplitude, and what it does is that it compresses the air molecules in front of it, and that's there. We can see the compression right there. When it compresses those air molecules, it then causes that compression to be pushed to the right, compressing nearby air molecules, which eventually cause compressions here, 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 and here, all the way down to the person or thing taking in the sound. Now, when a compression leaves an area, so for instance, when these guys decompress and push that way, what is left behind are these areas of expansion, these areas with less molecules in them. But the air molecules themselves don't move that far. They might move a little bit, as I said, like from here to here as they're compressed, but they're not going to move all the way down and travel with the sound itself. Creating sound. When you create a sound, you push air away from you, which creates a denser area of air molecules. This is called compression. That's what I was just talking about. When the air molecules expand out, they leave less dense areas behind, known as expansions. When the air molecules expand out, they leave less dense areas behind. This is known as expansions. So that's these guys here. So our expansions are left behind as the air molecules in front of them push forward. Compressions and expansions continue outwards as the sound propagates away from the source until it reaches the listener or runs out of energy. Moving sound. One wavelength is the distance between successive compressions. The harder the particles are pushed away from the source, the greater the air pressure change, otherwise known as the amplitude, and the larger the amplitude, the louder the sound is. Moving sound. The vibration of these particles can be better represented with a graph which shows changes in air pressure. High pressure is going to be our compressions, high pressure is going to represent our compressions, and low pressure is going to be our expansions. So we can see here in our graph our high pressure areas, or when our graph goes up, so these are going to be our compressions, and then our low pressure areas, these are going to be our rarefactions, or our expansions, as shown in this diagram up here on the top. The speed of sound. Sound travels faster in solids than in liquids compared to gases, and in denser mediums. So pause the video again and write down the answer to the question, why would sound travel faster in steel than in air? As shown down here. You can see the steel is going to move almost 6,000 meters per second, while in air it's only going to move about 343 meters per second. That's over 17 times faster in steel than in air. So why do you think that is? The molecules in steel are closer together. So think of the molecules looking like this in steel, whereas in air, they're going to be out here. And sound movement is all about one particle moving another particle, which moves another particle. Since the steel molecules are so close together, they don't need to move very far in order to bump their neighbor. Since it's easier to move their neighbor, our sound can travel really fast. Whereas in air, it takes a long time for particle 1 to reach particle 2 just because of its distance away from each other. Air is less dense, therefore the particles are further apart. Since it takes longer for particle 2 then to reach particle 3, the overall speed of the sound transfer is slower than it is in steel. The speed of sound in air depends on the temperature of the air it's passing through. Its speed increases by 0.59 meters per second for every 1 degree Celsius increase in temperature. The specific speed of the sound can be accurately determined using the following equation. V equals 332 meters a second plus 0.59 times the temperature, which is this guy right down there. So that's going to be our temperature. Check your understanding. Calculate the speed of sound in air when the temperature is 16 degrees Celsius. So we are looking for V. We know the temperature is 16 degrees Celsius, and we're going to use our equation. So let's plug our numbers in. V is going to equal to 332 plus 0.59 times 16, and that equals to 341.44 meters per second. Now we need 3 sig digs in our answer, so our final answer becomes 341 meters per second with no direction. Check your understanding. A string is vibrating at a frequency of 440 hertz. How many vibrations does it make when the sound produced travels 664 meters through air at a temperature of 0 degrees Celsius? Okay, so what do we know? We know frequency is going to equal to 440 hertz. How many vibrations does it make when the sound travels at 664 meters? We know the distance it travels is 664 meters, and we know the temperature is 0 degrees Celsius. Since we know the temperature, we can find the V, right? V is going to equal to 332 plus 0.59 times 0, which is going to equal to 332. So we're asked to find the number of vibrations. Remember, frequency is going to equal to the vibrations per second. So what we need to know is we need to know how many seconds it's actually traveling for. Now we know most of the information. So what we can actually use is V is going to equal to D over T. T in this case being time. Time is going to equal to D over V. Distance is 664 meters. The speed is 332. So that gives us 2 seconds. Since we know we're vibrating at 440 hertz or 440 vibrations per second, and we know the string is vibrating for 2 seconds, we know that there are going to be 880 vibrations total. A 200-meter dash along a straight track was timed at 21.1 seconds by a timer located at the finish line who used the flash from the starter's pistol to start the stopwatch. If the air temperature was 30 degrees Celsius, what would the time have been if the timer had started the watch upon hearing the sound of the gun? So to answer this question, we need to understand that the timer is starting at either at the speed of light or at the speed of sound. At the speed of light, we know that's going to be exactly correct, and it took 21.1 seconds for the runner to reach. Now, if they're doing it by sound, we know there's going to be a delay. We know the delay is going to be based on the amount of time it takes for the sound to actually be made to reach the ear of the person starting the timer. So we know that the distance is 200 meters. So that's how far the sound needs to travel. We need to know the velocity of the sound. We know it's 30 degrees Celsius. So we're going to do 332 plus 0.59 times 30. So we're going to get a velocity of the sound of 349.7 meters per second. So we need to know how long it's going to take that sound traveling at that speed to go 200 meters. So T is going to equal to D over V. 200 divided by 349.7 equals 0.572 seconds. So what would the time have been? Well, we need to take the total time, the real time, the 21.2, and we're going to subtract 0.572 because that's how long it would have taken the starter before the starter actually hit the stopwatch. So 21.2 minus 0.572 gives us a time of 20.63 seconds. Now we need 3 sig digs in our answer. We use 3 sig digs. The 200 meter, we're just not going to include in our sig dig, so it doesn't really make it as realistic. And we're going to go with 20.6 seconds as the time if the timer had used the sound to start the stopwatch. And that concludes our lesson on sound, sound energy, and speed.